Okay, big picture of where we're at. So let's go back to the, I think, I just want to review this slide with the, remember the oil leak, right? The oil leak. So remember we had the rate of change of oil entering the ocean, and then the accumulated volume of oil, like the net accumulation of oil leaked into the ocean. It's like meters cubed per day, that's our rate of change, and then meters cubed. So what is this kind of endeavor that we're on? You know how fast something is changing at every moment. How do we know that? What is that? We have a true rate of change function, actual rate of change. In the end, we want to know how much of it we have at every moment. And we're in some sense, we're going to hit a milestone today, and we'll explain this, of this process. We're going to hit a real important kind of point. Not the end, not the very end, but a really important part. So you know how fast something is changing at every moment. You know how much of it you have. You want to know how much of it you have at any moment. This is the process that we're on. Okay? And so the key to this whole thing is constant rate of change. That's why we worked on it for so long and so hard at the beginning of the course. Right? Given the rates, right, that's like a value of m, then we know that a dv is m dt. And that's our equivalent to dy equals m dx. And then from a little change in v, we could get, and as v initial, we could get a v final. Okay? So this is the core mathematics behind this endeavor. You know how fast something is changing at every moment. You want to know how much of it you have at every moment. So how is it? Given a constant rate, we have at any particular moment, we can assume essentially a constant rate, and we can calculate a little bit of accumulation using the dy equals m dx, or in this case, dv equals m dt. And then with dv, we can get a net or total accumulation, v final. All right, so that's how these core ideas that we talked about in week 2 or even week 1 of the class are now our central tools for this endeavor. You know how fast something is changing at every moment. That means you're given a constant rate. You want to know how much of it you have at every moment. We get a little bit of accumulation, and with little bits of accumulation, we can build up net or total accumulation. Okay? Oops, sorry. All right. So that's the big picture. Okay, so now what is this progression of functions where we're using this mathematics? First, we have exact rate of change, and then from that, what do we do? You said approximate rate of change. Is that right? Yep. Right? That's approximate rate of change. So we start with exact rate of change, and we break it up into intervals, and we get these actual rates, say, at the beginning of every interval. And you did this in homework a week ago. And then using those rates, the actual rate at the left side, or the beginning of every interval, we build the approximate rate function. Okay, and we call that just r, right? Just r. So this is a new function built from, or created from, the actual rate function, and it consists of constant rates. But that blue approximate rate function, it's trying to be like the actual rate function, just using constant rates. Why? Why do we do that? Because constant rate of change, all the mathematics of constant rate of change we're going to use now to start building changes of accumulation and then net or total accumulation. Okay, so exact rate of change. From that we build constant rate of change. So we did all that. And then from approximate rate of change, we do what? We built the a function. And so far, all we've done is build that a function piecewise, right? Piecewise. So in every interval has its own rule, right? Every interval. So for this first interval, we wrote the rule for the first interval. And then this second interval, we wrote a separate rule. And then the third interval, we wrote it still a second. So we had, for every one of these intervals, we had its own rule. So This would not be very convenient if we had 50 intervals or 100 intervals. We'd have to have a rule for every interval. Okay? So what is our goal in this, our sub-goal now in this endeavor, is to write this function, this A function, just with one line. Instead of a separate rule for every interval, we want to write it with one line. Okay? And so that's what we started talking about at the end of class Thursday, and you were working on some of the pieces of that in your homework for today. Okay? So what did we say? So we said that so here's the basketball, right? So same thing. We have the exact rate of change of the rocket's height with respect to time. We built the approximate rate, right, which is the function based on constant rates. And then from that, we built piecewise, we built the approximate accumulation function. Okay, but then we said, all right, so we're going to just kind of go back and look at this more in terms of, in order to build the one-line accumulation function, we want to think about completed delta t intervals and the current interval. Okay, so we think about time is increasing through these intervals. If we pause time at any given time, there would be all the intervals, the previous completed intervals for which we got accumulation, and then a part of the current interval for which we're going to also add a little bit more accumulation. Okay, so that's kind of where we left off Thursday, talking about the big picture. And so I think from there, we're ready to see how you're going to do on this quiz from Top Hat. So let's get Top Hat ready. Any questions about that overview, where we've been, what we're doing? Any questions? And my thing here is the black one at the bottom. The single black question mark. What is that representing? Yeah, so that's the current, we call that the current value of x. The current value of x. Okay? The current value of x, right? So that we can think of that as a length from the y-axis. Right now it's 12. Now it's 13. Now it's 14, right? So that's x, right? The current value of x, all right? What is the blue single question mark? Okay, what is this? This is the amount of change in the current interval, right? The amount of change in the current interval is what? dx, right? That's the amount of change of x within a moment. So in this particular animation, what's the domain of dx? What does dx vary between? So what does the value, dx is a width, right? It's a change in x. So what's the lowest possible value of dx that we're seeing here? 0. Every time we start a new interval, dx is 0. It goes back to 0. And what's the greatest value of dx that we see? 1.5. Right before finishing, or right as it finishes an interval, that change in x is 1.5. And so it's taking on all the values between 0 and 1.5. It's the amount of change in the current interval according to the current value of x. This is all super important. Okay, next. What is next? Oh, I think this one right here. So the single purple question mark has a width of what? Yeah, that's showing the most recent completed interval. The most recent completed interval has a width of, you should be thinking delta x. Delta x. All the completed intervals have a width of delta x. It's just this is showing the most recent completed interval. It's always jumping ahead. But all those completed intervals have a width of delta x. Remember we said delta x is a parameter. It's just, given our situation, it stays constant. It's how wide our moments are. But then dx varies within the width of delta x in the current interval. Okay, So I think the next thing is the double purple question marks. Double purple question marks. What does that represent? All of that's showing the completed intervals. And the gold double question marks, we call that the current interval, right? It's the interval that has the current value of x, right? It's the interval associated with the current value of x. All right, and what is the double red question mark? That's our exact rate function. Nope, not that one. This one. Exact rate of change function. That's where it all begins, right? You know how fast something is changing at every moment. It all starts with the exact rate of change function. From that, we build double black question marks. Approximate rate function, which we just called R. Let's see, I did it again. This one. And I think that was 7 things, right? Yeah, that's 7. Okay, so all really important terminology. We're looking at an exact rate function. We're building the approximate rate function, which is based on constant rates of change because we can do the math of that, right? dy equals mdx. And then with dy, we can build little changes. And then with the little change, we can build up the net accumulation at any value of x. That's what we're doing. We want the net accumulation at every value of x. That's a function, right? That's the a function. Okay, so now we're gonna figure out with this one. We've got all the tools to put together the one rule, one line version of that a function. I'm gonna do it today. Okay. And why do we need that? Because if there's 50 or 100 or 1,000 intervals, the piecewise version is very inconvenient. It would take way too long to write down. But with one line, it doesn't matter how many intervals we have. It'll be the same function for 1,000 or 1,000,000 intervals. Okay, so here we go. Let's do it. Maybe. Where is it? Here we go. Stay with me and ask questions. See, if I lose you, probably someone else got lost too. Don't hesitate to ask a question, okay? So this is again, you know how fast the quantity's value is changing every moment. You want to know how much of it you have at every moment. Okay, and so this is a paused version of what we just looked at, okay? A paused version of what we just looked at. But always think about x increasing through the intervals, right? X is increasing through the intervals. So we're going to pause it and analyze the paused version. X is a variable, right? X varies. X varies. So let's talk about how much we have at x equals 6.75. That's where I've paused life here as this x is increasing and the approximate rate function is being generated from the actual rate function. So we're going to pause it right here at 6.75 and ask how much do we have at x equals 6.75? So answering that question means, in general, doing what? So this is what we talked about at the end of class last time and you worked on in your homework. What does it mean in the broadest sense to be able to calculate how much we have at x equals 6.75? Any volunteer? This is, yeah. What's that? So add up what? Okay, so intervals are objects. We're not adding intervals, but we're adding something about the intervals. What are we adding about the intervals? We're adding rates of change together. Are we adding rates of change together? Not quite. Yeah, we're adding bits of accumulation, right? Which we get from the rate of change, right? dy equals mdx, right? So we're adding a bunch of bits of accumulation. And so we've got what? We've got completed intervals and we've got the current interval, okay? So a of 6.75 is going to be the change from the completed intervals. In this case, there are 3, right? We're starting at a, starting at x equals a, down here. So here's the first interval, second interval. The third interval is the one I'm showing as delta x. And then what? And then the change from the current interval. So we're gonna calculate the little bits of accumulation from the completed intervals, and then a little bit more from the partial interval. in the current interval, right? The partial, the dx width within the current interval. So this is the overall strategy. Change from completed intervals plus change from current interval. Yeah, I sure hope so. Yes. Thanks for asking. So this is the key to forming the one rule version of the A function. Change from completed intervals plus change from the current interval. Okay, so the question is, now let's start with the change from the completed intervals. We need to get these x values to get the right rates for each interval, right? So what x value are we going to use to get this rate right here? What x value are we going to get to use this rate right here? So we want the rate, what, at the beginning of that interval. So that corresponds to x equals a. So if I put a into the rate function, I'm going to have that constant rate. What about the second interval? So the second interval, what x value am I going to plug into the second interval to get this rate right here to be the constant rate for the whole interval? So how would you express that x value right there? He said a plus delta x. Agree with that? Yeah, because it's going to be a, and then we're going to want delta x more, one interval more, and that will be the x value. So we had a in the first. A plus delta x will get us to the left side of the second interval. We'll plug that into R, and we'll get that actual rate, and we'll apply that to the whole second interval. Okay, what about the x value for the third? Yeah, so we're just going to go another delta x over, right? So we're going to do a plus 2 delta x. That'll get us to the left side of the third interval. So what we want now is a general formula for this x value that's going to go into the rate, so that if we had 100 completed intervals or 150, we would know, like, say, the 88th interval, what that x value will be at the start of the 88th interval. So we need to kind of develop a little formula here for that x value. And so for these completed intervals, what we want to use our summation notation that we've learned, right? Because if there's 50 or 100, then we don't want to write out 50 or 100 things. So this is where summation notation is not scary, but it's helpful, right? Because they all look alike. They're all a rate times delta x. So instead of writing that over and over again, we can just write it once and have a notation to say how each one's a little bit different than the others, okay? But they're all of the form rate times delta x, and we're going to sum a bunch up, right? So the question is, what's a formula for that x value of the rate, right? So what's the formula for the x value of the rate? So look, we're called j is going to be the interval number. So j is going to start at 1. Okay, so that first interval has the left side at x equals a. That's the first interval. Let me draw it again down here. Here's a, and so here's those 3 intervals, say. And so here, this is j equals 1 is the first interval. J equals 2 is the second interval, and j equals 3 is the third interval. So j, the index on our summation, is standing for which interval we're talking about. Okay? So look, when we're in the first interval, our x value is a. When we're in the second interval, it's a plus delta x. When we're in the third interval, it's a plus 2 delta x. Because if we want the third interval, we got to go a plus 2 completed intervals gets us right there. Gets us to the left side of the third interval. So if we wanted a formula for the jth interval. So suppose there's a lot more down here. Dot, dot, dot. And here I am in the jth interval. I want that x value right there. Can you figure out how to write an expression for that x value at the left side of the jth interval based on the pattern that we're seeing here? So the second interval, to get to the left side, a plus 1 delta x. The third interval, to get to the left side, a plus 2 delta x. So how are we going to get to the left side of any interval, say the jth interval? Yes, sir. Okay, so is the x value j minus 1? What is the x value? What's the x value? You're onto it, but j minus 1 isn't the x value. What is the x value? Yeah. A plus j delta x. Is that right? No, a plus j minus 1. Right, just got to put it together. Yeah, so put their two answers together and we'll get it. We're going to start at a, and we're going to go what? One less completed intervals to get to the left side of the jth interval. So to get to the third interval, we need to go across. Look, to get to the third interval, how many intervals do we need to go across? 2. To get to the 10th interval, how many intervals do we have to go across? 9. To get to the 25th interval, how many intervals do we have to go across? 24. It's always one less, right? Yes, ma'am. Because we want j to mean the interval number. It's a lot easier to say, like, it's a little more confusing to think of this as 0, 1, 2. It's a lot more convenient to think, oh, 1 means the first interval, and 2 means the second interval. But yes, we could do that. We could do that. But this gives a little more meaning to j, and doesn't, we don't have to subtract or add 1 to j. So by starting with 1, it can be the interval number. And then we need to go across what? J minus 1 intervals to get to the left side of the jth interval, which will be the x value we need. So this is how, what is this? This is the x value of the left side of the jth interval. A plus j minus 1 of delta x's gets us to the left side of the jth interval. All right, and so then that's going to go there, right? And I want to make that smaller because we don't want to lose sight of what is this thing summing up. It's still summing up what? Calculated how? Right, accumulation calculated by? How do we calculate summing up? What are we summing up? Nope, we're summing up little bits of accumulation. You have to see, summing up little bits of accumulation. Each one, m dx, but now delta x, because we got full moment intervals, right? Full moment intervals. But, so I'm going to make that thing inside smaller so you don't lose sight of the big picture. Because when you make it all the same font, it's hard to see, right? And that's maybe in the book. It's a little hard to bring out. Because then you see these two delta x's next to each other, and you're like, what's going on, right? So this x value is slightly less important, right? So it's like a secondary. It's important. But what's more important is that you see that this is the sum of rate times change in x. Rate times change in x. And it's just that we need that expression to get us to the right x value to get the rate we need for the jth interval. Okay? So that stuff that's smaller is secondary. What's first is that you see this is the sum of delta y's, or rate times delta x. Okay, so we've got the sum of the completed intervals, right? We got the sum of all the change from the completed intervals. M delta x plus m delta x plus m delta x plus m delta x. Okay? So now let's talk about the current interval. So the question is, how many completed intervals to reach the current interval? How many completed intervals do we have to go across to reach the current interval? So in this case, it's 3. But in general, how many is it? How many of the completed intervals? Maybe I should ask it that way. How many of the completed intervals do we go across to get to the left side of the current interval? How many of them? How many of them? So we have a bunch of completed intervals. how many of them am I going to go across to get to the left side of the current interval? All of them, exactly. We're going to go across all the completed intervals, and that'll get us to the left side of the current interval. Exactly. We're going to go across all of them, whatever number that is. In this case, it's 3. Okay, so thus the x value of the current interval, for the current interval, the x value is a plus what? Total number of completed intervals times delta x. So in the completed intervals, it's going to be j minus 1 delta x's to get to the left side of any particular completed interval. But to get to the left side of the current interval, we're just going to go across all the completed intervals, and then from a, and then we'll have it. So it's the same type of thing as a plus j minus 1 delta x, but the difference is now it's just whatever total number of completed intervals we have. Okay, that little expression right there is a function we call left of x. Left of x. So what? It's a function. This is a function, the name of which is left. So this is what? For the current value of x, right there. Left of x, so this is a kind of a different function than what we're used to because it doesn't give a y. What does left of x give? The dependent variable of left of x is what's going into r? Another x value, right? So the dependent value of r is another x value. You put in an x, it gives you back another x. This is different than most functions you've been used to, right? In most functions you've seen, you put in an x, it gives you a y, or it gives you some other, the value of some other quantity, right? The left of x is different. You give it an x, it gives you another x back. And which x does it give you? It gives you the x value at the left side of the current interval, or the starting x value of the current interval. Super important. It does not give you a rate. Left of x doesn't spit back out a rate at you. It gives you back another x, right? This key x here. And then we're going to take that x, which is left of x, and we're going to put it into the rate, and we're going to get the constant rate for that interval. So try to remember, left of x, it takes a value, it takes the current value of x, and it returns, or its dependent variable is whatever the x value is at the start of the current interval, right? Why we need that? Same reason we needed all the other x's to get that constant rate defined by the start of the interval, this one here. But it's not until we take left x and evaluate r at left x that we get that rate. Left x is not a rate of change. So we're going to do that. We're going to take left x and we're going to evaluate r at left of x. And now that is this rate here. R of left of x is this rate here. But left of x is the x value. It's the x value that we're going to plug into r to get the rate. So all that's really left in this, so we've got most of it here. All that's really left is to figure out how many, given a value of x. What is this? Right? So what is left of x? How do we? So we know what we've defined it. We know what it means, but we need to get a rule for it. What do we do with x? What do we do with x? What algebraic process do we do with x to get left of x, to get that x value that's now highlighted in red? And once we have that little sub-function, right, so it's like a function within this function, then we can write, we're pretty much finished writing the one-line accumulation function. So we're going to spend the next little while talking about figuring out what is this function left of x, okay? What is the algebraic rule for it? So here we go. So here is familiar, just a different version. This is to help us kind of figure out what left of x is. So my starting value to accumulate from is a, that's 1.3. I've set my delta x to 0.62. And then the blue line is showing the current value of x. And you see the rate function. You see the rate function being generated there as x increases. So this is left of x. It's always showing the current value of left of x, right? It'll stay constant as long as x is in a particular interval. It's going to stay there, and then but when x moves into the new current interval, then it changes. This is what we're after. What's a formula that we can plug in x into, and that formula will tell us what this x value is at the left side of the current interval. So let's just pause it here somewhere along the way. Okay, how about no? Okay, so I've paused the generation here of the function, and we got a is 1.3, delta x is 0.62, and the current value of x is 7.3513. And so what I want you to find is, can you figure out what is, so really, so what did we say? We said left x was what? Let's write that out. Left x was what? It was a plus what? The number of completed, all of them, right? All of them, all the completed intervals, times what? Times delta x. So really, what we're really interested in is this. Okay? So I want you to tell me right now, for this paused value of x at 7.353, how many completed intervals are there? How many completed intervals are there? And I want you to do that any way you can. Any way you can figure that out, it's fair game. How many completed intervals have we had so far with this current value of x at 7.3513? Go. Any way you can do it. Do it. Any way you can do it. Fair game. No rules. Just figure out how many completed intervals there have been. And then once you know that, then I want you to compute left of 7.3513. So 2 questions. How many completed intervals? You can how many completed intervals at this paused value of x? How many completed intervals? Most people are saying 9. Did you get 9? How'd you get 9? Oh, you just counted them? Oh, you weren't allowed to do that. I'm just kidding. Yeah, I said you could do anything. Yeah. Count them. Yeah, you can count them. 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, so that therefore, if there's 9 completed intervals, what is left of 7.3513? What did you get? What's that? 6.88, okay? Is that a rate? Is that up here, 6.88? No, it's x value, right? So what is it? To get to that x value right there with the finger pointing at it, we're going to go over A, right? First A, and then we know it's 9 intervals, and each interval is how wide? It's going to be 9, what? 9.62s, right? 9 0.62s across there, plus A is the 1.3. So 1.3 plus 9 widths of 0.62 equals 6.88. Look at the graph. Does that agree? Yeah, here's 7. It's shy of 7, right? Shy of 7, 6.88. Remember, what does left x do? It takes an x value and gives you back another x value. Which x? The x value at the left side, or the starting value of the current interval. Okay, let's do it again. So this is the real question. So can we come up with a mathematical formula to get the number of completed intervals? So someone in the back, someone new. Did you come up with a formula? Yes, sir. Oh, no, way in the back. Yeah, go ahead. Okay, so x minus a would mean what? What quantity would x minus a give us? So this 12.718 minus 0.65, what does the answer to that represent? Just that much. Good, well said. The change, that's the whole change in x from a to x, right? The whole change in x from a to x. It's like that whole distance across from a to x. And then you wanted to divide by delta x. What does that do? So we've got this whole one change, and we're going to divide it, what, by 0.38, which is, why does that work? Yeah. Not rate of change. Right. Okay, yeah. So it's taking that whole distance, and we're saying how many distances of 0.38 would fit into the whole big distance, right? That's division, right? How many of the distances 0.38 would fill up that whole distance? And so when you do that calculation, what do you get? Nice and low. 31.76. Someone else get that? Just to be sure? Okay. So there's 31.76 completed intervals. Is that right? No. How many completed intervals are there? 31. So from the 31.76, we want to get, say, there's 31. What's the 0.76 represent? Yeah, good. So it's not the distance. It's not an x unit, but it's like the percent, right? So it's like we've gone 76% into the current interval. We don't care about that, right? We want to know how many completed intervals there are. So what we really need is we need to, so notice that we're not rounding 31.76. If you rounded 31.76, you'd get 32. That's not what we want. We just want to say whatever decimal is added on there, that's the percent that we are into the current interval. We don't want it because we want to know whole intervals. So we just want to cut that off. We just want to, boom, right? Because this is the percent of the current interval. 76%. And we don't care about anything to do with the current interval here. So what did we do? We took x minus a, and we divided by delta x, and that gave us the number of intervals along with the percent of the current interval. And then we want to chop off the decimal. Well, there's a mathematical function that does that called the floor function. The floor takes any decimal value and gives you the greatest whole number less than that one. Cuts off, it just chops off the decimal portion. So you write that this way. Floor function, you write that like this. And this is called the floor function. What does the floor function do? It gives you the greatest full value less than the value you give it. In layman's, or the easy way to think about it is it just chops off any decimal and gives you the whole amount. Even if it's 31.998. not 32, it's still 31. So this does it, right? So this gives us the floor function of x minus a over delta x gives us the number of completed intervals. So we've got 31 now. So there's two different things going on here. There's the number of completed intervals, and then there's left x. So what happens is, come 2, 3 days from now, a week from now, our experience is students mix those up. There's two different things. We've got the number of completed intervals. That's this thing in blue, the floor function. Then we use that. That's part of the left x formula, right? To get left x, we got to do a plus all that distance, which we get from the number of completed intervals times delta x. So make sure it's really easy. There's so much new material here. It's really easy to get those two things confused. So try to organize it in your mind. Left x uses the number of completed intervals, or uses the floor function to get that x value at the start of the current interval. So what is it? It's going to be, left x is going to be a, our 0.65, plus our 31 intervals times width of each interval. And what is it? Anyone got that? And does that agree with the picture? 12 point, here's 12, here's 13. It looks, oh, right, and so this is it right here. Left x is right here. Not quite halfway from 12 to 13. So again, left x is the x value at the start of the current interval. Part of getting that is getting the number of completed intervals, which is what I've done over here in blue. That's the floor of x minus a over delta x. Get the total width, x minus a. Ask how many intervals have width delta x, that's division. Chop off the decimal, that's the floor part. And that, in this case, that gave us 31. And then we can use that 31 to get left x 12.43. Distance. What's the distance? Right. So it's going to be the total distance across from A to X is 13.494 minus 2.39. Total distance across from A to X. And then we want to know how many intervals are there. How do we get how many intervals? Divided by, why am I not doing this in GC? Here we go. I'm going to take 13.494 and subtract, is it 2.39? And divide by 0.12. What is that telling us? 92.533 is telling us intervals including what? Including how much of the current interval we're going through. Okay, so I'm going to copy that. And to get floor in GC, you just type out FLOOR, and then those brackets appear. So now I just copied that expression. I'm going to put that in, or I could just put in 92.533. And look at, what does it tell us? Chops off the 0.533 and makes it 92. Okay, so left of x is 92. No, that was just, we just counted the intervals. We just counted the number of intervals. So from here, what do we need to do? Yeah, so, okay, so left of x uses that to get that where we're pointing at, right? We need that x value at the start of the current interval in order to determine the rate in that current interval. So it's going to be, let's do it, A, which is what? 0.39
plus 92 times 0.12. 2.39, thank you. And it says 13.43. So our x value was 13.49. Does it make sense that left of x would be 13.43? Yeah, because the intervals are so small now that it's going to be very little distance back to the left side of the current interval. Okay, so before we go back and finish the big A equation, let's just preview coming attractions. Notice what happened. Can you see the approximate rate function now for this very small interval? Let me turn off. So I'm going to turn off the actual rate function. That's not it. That's it. So that's the approximate rate function for a very small interval. What do you notice? This is doing a really good job mimicking the actual rate function. Preview of coming attractions. Okay, so let's go back and we'll finish the one-line function. Here we go. So, how much do we have at any current value of x? What is this A function? Okay? What's the big picture structure of the A function? So if you just in its overall structure, summation of what? Are we summing up rates? Little bits of accumulation, right? We're going to sum up little bits of accumulation, and those are broken up into two different kinds, right? The first is from the completed intervals, and then a little bit more from the partial interval and the current interval. Okay, so we got accumulation due to completed intervals, and we already did that, right? It's the sum of all these rates times delta x, all these, which is changes in our quantity, little bits of accumulation. Don't tune out now. Plus the accumulation so far in the current interval, which we said was we're going to take that left value at the current interval and plug it into R to get the constant rate for the current interval. All right, and then what? So notice, what is it times? Not times delta x. Times dx, because we've only gone as far as dx in that interval. So that last rate that we were just doing when we were doing left of x, and r of left of x, only applies across dx, not the whole delta x. Important distinction, do you see that? But it's still rate times the change in x. It's just a smaller change in x. So we just have a few more things to add on here. So if we want to have any number of intervals, right? So now the number of completed intervals can be any number of intervals. How do we write an expression for the number of completed intervals between a and x? What is the expression for how many completed intervals between a and x? One more thing. Floor of that. That was what we just did, right? The floor function. So that's going to be the last one we do is going to be the number of complete intervals. So we're going to go from j, starts at the first interval, to all the way to the number of them, which is the last one, right? So then j is going to cycle through every value. J will be 1, and we'll calculate that change, r times delta x. Then j will be 2, and we'll calculate the r times delta x. Then j will be 3. And then j will be 4, all the way up to the last one, which will be the x minus a delta x interval. And then we're going to add up all those bits of change. That's the summation. So you got to, when you see that, you got to think, okay, j is going to be 1. I'm going to calculate that. J is going to be 2. I'm going to calculate that. J is going to be 3. I'm going to add all those up. Okay? And then the only thing left is we want a function of x here. We want a function of x. So we don't want dx in our formula. We want just x's. So what is dx in terms of, how can you rewrite what dx equals using x? What is that change using x? Right, it's going to be final x minus initial x, which would be x minus left of x.
that's another way to write dx using x, our independent variable.
Congratulations. Ta-da.
You got it. It only took one class period, right? Or 1 month, however you want to see it, okay? All right. So this is the one-line version of the approximate accumulation function. So it's important that you see the big picture first and foremost. The big picture first and foremost. And then as you get more into the minutia of it, it gets kind of less and less important. And so we don't want to get distracted as much. We never want to lose sight of the big picture, which is what? Completed intervals. Yep, this whole thing right here is like m times change in x. And we're going to do that for each complete interval. And the way we cycle through that is by the value of j. When j is 3, that's the third completed interval. When j is 6, that's the sixth completed interval. It's going to calculate m times the change in x. Each individual interval, j equals 1, j equals 2, and then add those all up until we get to the number of completed intervals. And then we have a little bit more accumulation, and that's going to be the rate at left of x, the rate here, times dx, which is just can be expressed as x minus left, final minus initial. Okay, one more reminder. Number of completed intervals. That's the floor function. You should know how that we derive that. We know what that means. Left of x is a plus that thing, number of completed intervals, times delta x. Make sure you know the difference between the number of completed intervals and how we use that. We use that to get the x value at the left side of the current interval. And what kind of value is left of x? Another x. It's not a rate. We take that and we put it into the rate function to get the constant rate, the r of left of x. Okay, so quiz again Thursday. Sorry, exam is next Wednesday night. We're on track. So quiz Thursday, post the practice quiz. And we're going to do a little bit of homework